Well, it's a real pleasure in such a magnificent crowd. Real pleasure for me to introduce Dr. Steve Charles as this year's Charles L. Schepens MD Lecturer. So Dr. Charles is Clinical Professor of Ophthalmology at the University of Tennessee College of Medicine, and he's Adjunct Associate Professor in the Department of Biomedical Engineering at the University of Tennessee. As well as an ophthalmologist and a retinal surgeon who's performed nearly 50,000 vitreoretinal surgeries, Dr. Charles is a mechanical and electrical engineer with over 200 issued or pending patents and has developed many of the techniques and devices used by vitreoretinal surgeons worldwide. Dr. Charles's impact on surgical technology does extend well beyond ophthalmology. He's the founder of Microdexterity Systems, which developed robots for dexterity enhancement for minimally invasive knee and hip replacement and skull-based neurosurgery. So Dr. Charles has been recognized with the Herman Wacker Prize from the Club Jules Gonin, the inaugural Founders Award from the American Society of Retina Specialists. He's delivered the American Society of Cataract and Refractive Surgery's Charles Kellman Innovations Lecture, quite the interloper. And in 2018, Dr. Charles was named the American Academy of Ophthalmology's Laureate Awardee. So Dr. Charles has been one of the most prolific and influential innovators in ophthalmology and retinal surgery. So please join me in welcoming and congratulating this year's Charles L. Schepens MD Lecturer, Dr. Steve Charles.
I don't know where he got all that information. Well, thank you so much to the selection committee for picking me and for the organizers of this absolutely fantastic meeting. I'm as nervous now, almost as nervous as I was when Schepens came to watch me operate at the NEI 50 years ago. So what I'm going to do is kind of go through, I consult for Alcon, financial disclosure, I'm not advocating any products. Charles Schepens basically created the specialty of retina. Before, everybody was a comprehensive ophthalmologist, and we owe him a tremendous debt of gratitude. He emphasized retinal drawing. He obviously did not invent scleral buckling, but was a tediously great surgeon. He brought us the binocular indirect ophthalmoscope, so we're all indebted to him. I found when he came to visit me at the NIH, he was incredibly studious. He was making elaborate notes and asking 1,000 questions, but he was extremely gentlemanly, even though I was obviously nervous having, the master watch me. So I'm going to talk a little bit about the development process. I'm an engineer, as Stephen said in his very kind introduction, and but we work with many engineers, and I'm trying to make a couple of points. One is the techniques and technologies are not independent of each other. They're highly interdependent, and they must evolve in parallel. Secondly, ideas don't come from committees. You don't do a market survey and come up with a product. They come typically from one surgeon talking to one or two engineers, the initial idea. But as the complexity increases, we need more and more engineers, more and more engineering. So just in medicine, as we have subspecialties, there are many subspecialties in engineering, and you need very large teams as the complexity increases, as you'll see in subsequent slides. So engineering is absolutely critical to developing these new technologies, and close collaboration is critical. It's not about the doctor getting credit. I did this, I. It's about engineers getting credit as well. I'm going to make a point of naming and crediting many engineers in this talk. They must educate each other. Engineers don't know medicine, and surgeons don't know engineering, and you got to do both to get it right. The cost is exponentially growing as complexity grows. So as good as the NEI is, they can't fund all this. They can't fund much of any of the product development. So it comes to companies to do this work, and we've got to figure out a way to work with them in a full disclosure ethical method. They offer so many things, not just capital, more than you can get from philanthropy or from the academic environment, but they bring regulatory, global marketing, service support, so many other things to the table. So we got to work with them, we got to work carefully. Again, Schepens obviously created our retina specialty, including the binocular indirect, which he brought us. Robert Mockemer developed vitrectomy. Sometimes we get confused with who developed a device and who developed a specialty. Mockemer brought us the specialty of vitreoretinal surgery, along with John Marie Perel, engineer. Conor O'Malley, along with Ralph Heinz, engineer, brought us three-port vitrectomy. I worked with Clinitex on endophotocoagulation, and a number of engineers. Frankly, I haven't kept track of them, and I didn't put their names, so I apologize for that. I've worked with Carl Wong to develop the disposable cutters at MidLab, and then at CooperVision with Carl Wong as well to develop linear suction. And then many, many engineers at Innovision, too numerous to mention, and at Alcon, an even larger number on Acris and Constellation. So the engineering teams grow. As you see here, we've had extraordinary progress over the 50 years I've been doing vitreoretinal surgery, attributed again to these many engineers I've listed, and more surgeons I'll talk in upcoming parts of the talk. We've gone from 200 cuts per minute to 30,000. We've had cutters that weighed 900 grams, tremendous hand fatigue. Now they're 5.3 grams. The fluidics response time was over 2.5 seconds. Now it's 5 milliseconds. Console functions have grown from 3 to 13, the complexity I alluded to, and tool diameters changed dramatically from 17 gauge in the Machromer era to 27 gauge in many instances now. Machromer was, again, John Murray Perel, brilliant engineer at Bascom Palmer, that developed the first fiber optic endo-illumination, which is a crucial part of vitrectomy. Anton Banco, although he invented and patented the first vitreous cutter, never commercialized it. It's not about patents, and it's not about a CV. It's about products in the marketplace that we can use, and it's about training people to use them, as Machromer and Schepens both did very well. Again, Conor O'Malley and Ralph Heinz developed the 20-gauge three-port system. It wasn't self-sharpening, and it wasn't disposable, but it was very lightweight, pneumatically powered, and a big advance. Then Carl Wong and I developed the first disposable cutter, which was pneumatically powered, but it was also self-sharpening, which in some ways it's tied closely to the notion of being disposable. And then I developed dual actuation with, ultimately with Alcon, which again was self-sharpening and disposable. What about aspiration fluidics? With Machromer, who trained me, we had a syringe in the hand of an assistant. That's like having somebody you're arguing with driving the gas pedal and you're driving the steering wheel in your car. It was pretty bad. And so we would then move to a rack and pinion drive in the surgeon's hand when we used full function probes. Kind of awkward, and I'll show you that in upcoming slides. But the big advance came from again, Conor O'Malley and Ralph Hintz with the foot pedal control vacuum. It was only on-off, but it was foot pedal controlled, which freed up both hands to do endo-illuminator one hand and a variety of surgical instruments in the other hand with the infusion in the third port. Huge advance. Fluidics got faster and faster. I won't go over the details here in the interest of time, but they're listed there for you to read. This is my first patent, and this is a way to drive a syringe yourself. So it was the notion of surgeon control, but again, pretty awkward compared to Conor O'Malley's invention of a foot-controlled vacuum, which was made better when we developed a linear aspiration. So the foot pedal went up and down to control the vacuum level, which we're all familiar with now on both phaco and vitrectomy machines. And then with the MidLab system, we continued that, and with faster fluidics, and this trend continued. Systems integration was in the title of my talk, and this just means many systems in one box. I built a system called Innovision. I'm not any good at finance, and this company wasn't successful as a company, but Alcon acquired it, and that led to the Acris and Constellation. So a nice stepping stone, even though financially it wasn't what one had hoped for. And the Acris was at a high level of systems integration, but it didn't have a xenon light, and it didn't have an integrated laser. It's not systems integration to paint the box the same and put it on top of another box. They need to be integrated on the user interface and power supplies, et cetera, and in one housing. And that was accomplished, of course, with the Alcon Constellation. Let's talk about membrane peeling. Machromer had the courage to try that first, peeled an epimacular membrane with a bent needle. Well, but that had a sharp point, and if you look on the left, those are the reasons we changed to upgrade. Conor O'Malley, who doesn't get proper credit for it, invented the pick. So it was a nice, rounded, smooth instrument to peel, but you had to find the outside of the membrane. And then I developed forceps membrane peeling, which then evolved Diamond-coated forceps had a better purchase on it, but they didn't really grip at the end, which was a problem. And Klaus Eckhart came up with the idea of truly in-grasping forceps, which were better. And then I came up with the idea of them being rounded with the same radius of curvature of the retina, hence conformal, which also helped. Yeah, thank you. I have xerostomia, so I really need that. Thank you. Dry humor, dry mouth. So we moved to the conformal forceps, and then credit goes to Grieshaber, a Swiss company that Alcon ultimately acquired, and that worked closely with Dyson Higginbotham. Again, another absolutely brilliant instrument maker. Not an engineer per se, but a brilliant instrument maker that brought us the disposable forceps that are very lightweight, and because they're disposable, they always work, unlike reusable ones that get beat up in the autoclave. And they grasp right at the tip for epimacular membrane surgery, etc. Now, when membranes are highly adherent, membrane peeling doesn't work. So Makamer tried to peel those with a bent needle, which really wasn't a good technique in high adherence situations, namely diabetic traction attachments. So I came up with scissor segmentation, cut it up and leave it there. And then I came up a couple years later with scissor delamination, not cut it up, but cut it off. So remove it from the retinal surface in a different plane. And that was made better when we finally got curved scissors that work well because they had the same radius of curvature of the retina as depicted here. So this is inside-out peeling. There's the core vitrectomy doesn't even exist in traction attachments. And in this patient, we were able to delaminate inside out, this virtual patient, and then remove the posterior hyalate face at a separate step. What about air gas injection? Makamer literally put a needle in the eye, deflated the eye, turned a stopcock, and blew it out with air. So you had a needle in the deflated eye. So I developed fluid air exchange so you could pump air in as you remove fluid. So it was a normotensive step that allowed a complete exchange of the fluid space for an airspace. And Gary Abrams came up with an iso-expansive gas mixture so we wouldn't have these, it was a tiny small bubble or extravagant interocular pressures in the middle of the night, which had blinded some eyes. So credit goes to Gary Abrams for that and Brooks McEwen for giving us the air pump. Then some engineers at Altvis worked with Alcon for automated gas mixing and filling of the syringe. So this is what fluid air exchange looks like. All the surgeons in the audience are aware. And air gas exchange also is, again, a normotensive process that allowed a complete scavenging or exchange of that cavity so that you really got the mixture you want. And I developed air silicone exchange, so instead of injecting silicone in and trying to figure out what to do with the air, if you vent properly, you can have a completely, again, normotensive procedure and inject oil into the eye and get a complete fill reliably every single time if you do it with this method with air first, instead of trying to inject oil in a fluid-filled eye. What about subretinal fluid? Obviously, for many, many years, dating back to Gonan, the drain was transscleral, and that's what Makamer did during vitrectomy. He did 4 traction sutures of perotomy and a cut-down drainage, but I invented the idea of endo-drainage so that you put a device through the break or through a drainage retinotomy to drain. First, I did that with a flute cannula, 20 gauge, but that was kind of awkward, then tapered. But Sandy Grizzard and Harry Flynn, working independently, came up with soft tip cannulas. And our friend Stanley Chang, who's brought us so many fantastic accomplishments, and is this year's laureate winner, congratulations, brought us PFO, liquid fluorocarbon, for many, many different things. It made mastery of giant breaks just totally incredible, but also allowed us to drain subretinal fluid surgically when there were small breaks or you didn't want to make a drainage retinotomy, so a very useful technique. Of course, the move from single port to 3-port was a tremendous advance because now infusion was put in first and taken out last. It was always there. It allowed efficient exchanges, but it allowed us to do tool swaps instead of having a full function probe like Makamer or Duvas had, where you had to have it in there in the eye for a light source and for illumination. Those were present through the other ports, so you could exchange the tools. The trocar cannula system came from Dyson Higginbotham, again, an instrument maker who at the time was at Duke that I mentioned, and it later was adapted to 25 gauge by Jean Dewan, and then to 23 gauge by the Door Company, and ultimately 27 gauge by Alcon. I've invented a number of PBR techniques which were highly dependent, as I mentioned in my introduction, on the technologies that we have. namely high-performance fluidics and very fast cutters. And I'll go through some of these very, very quickly. Forceps are a better way to membrane peel than spatulas, and you start in the middle of the star fold. The anterior loop traction, which are radial fibers that pull the equator of the retina forward in PVR cases, is not a membrane. These are pre-existing vitreous fibers that are contracted. You can resect those with a cutter, and that works quite well. Subretinal surgery. Machromer developed that simultaneously and independently with me. And you can do it either through a retinal break if it's properly positioned to get these annular rings, so-called napkin ring, or if it's not positioned in the right location, but it's tending up the retina where you must remove it, you can do a mini retinotomy without removing any retina material at all. I don't even use diathermy for that. And this allows you to actually have retina apposition once you remove it. It's very, very nice, very small wound. Machromer did circumferential retinotomy, whereas I developed retinectomy. These, again, were developed independently and simultaneously. What's the advantage of my method, retinectomy over retinotomy? You remove all the tissue anterior to the cut. So the epiciliary tissue, neovascularization of the iris and anterior segment, all of these are less. PPR recurrence are less if you remove all the dead tissue that is circumferential, so-called relaxing retinotomy would leave in place. So that led us to interface vitrectomy because I did my retinectomies under air. I do retinectomies under oil, and Stanley Chang taught us how to do them very nicely under PFO, incrementally, carefully, so you don't end up with PFO in the subretinal space. So these interface vitrectomy, operating under air, operating under oil, operating under PFO are very effective. They keep the retina stable. They allow recognition of existing traction. They confine bleeding to the interface, which is nice. Vitrectomy under air actually works, except if it's an aphakic eye and they have striated keratopathy you can't see, or if there's a capsule defect and they've had anterior removed, you get fogging. So there's limitations. Reoperating under oil, I see many, many patients that had a 5-hour operation, took the oil out, operated, put in PFO, took the PFO out, put oil in. 5 hours later, they're done, when they could have just done the entire surgery under oil. It works very well. I've done that for 40 years, or 35 years, I guess. You can peel membranes under oil nicely, not just in a PVR setting, but epimacular membranes works very, very well. And it's, again, saves time, and if you know you're going to have to leave the oil in because of sort of recalcitrant PVR, peel the membrane, get rid of the epimacular membrane under oil. Works very nicely. Last procedure I want to mention is the retinopexy and endophotocoagulation for retinopexy, to restate that. Machromer used transscleral cryopexy, 360 paretomy, trap all the muscles, which none of us do in vitrectomy today unless we're doing combined buckles, which I don't do. And he used diathermy for hemostasis. I developed first as xenon, and I'll show you a picture of it, endophotocoagulation, which is the best way to do hemostasis because it doesn't cause widespread retinal necrosis resulting in so-called atrophic breaks. So it's safer than diathermy to use laser for that. We all use laser to treat retinal breaks and drainage retinotomies, of course, and we all use it for PRP. And it's evolved technically. The first unit, when I was at the NIH, which is where I got my start after learning vitrectomy from Machromer at Bascom Palmer, I took the xenon photocoagulator depicted here that Meyer-Strickerath developed with Zeiss, and I built the device on the right with an engineer called Charles McCarthy. Built it in a week, tried it on the machine, tried it on a patient. Within 3 weeks of starting the concept, things were a little simpler in regulatory space in those days, and it worked extremely well on the very first patient. So we treated retinal breaks and did PRPs with this adapter. 18-inch fiber, very awkward ergonomically, but it worked. And then we adapted. Connor O'Malley's brother, Patrick, developed this parabolic refractor xenon arc source. So we developed a device that was commercialized and used for a couple of years before myself and several, Jay Flashman and several others simultaneously developed laser sources for it. But it worked well with xenon. It's just better to have a thin disc laser like we have in the current Constellation device. Well, I'd like to thank the Academy and thank the selection committee. And again, fortunately, for once, I didn't run over the time, and I appreciate very much this honor. Thank you all so much.
Yeah, absolutely. So, Dr. Charles, on behalf of the Board of Directors of the Retina Research Foundation in the spirit of the Schepens International Society, it is my pleasure to congratulate you, and today as the recipient of the C.S. Charles Schepens Award, it recognizes your outstanding contributions to retina research and wish you the best in your continued work. I do especially want to remember Dr. Alice McPherson, a pioneer in the field whose own work has contributed so much to us and has made this award possible. So, Dr. Charles?
And I'd like to second that with Alice McPherson. It's done a ton of money for research. Just one.
Yeah,
Thank you so much.
Yeah, it's time now for the refreshment break, and if you could all get back here by 10:45, we'll start with the cases. You don't want to miss that. Thank you.